Good afternoon. Good afternoon. Hope everybody's doing all right. Everybody's doing great. All right. Looks like everybody's in. All right. Hope everybody had a great weekend. Hope everybody's doing all right. Ready to get this week started. Did anybody have any general questions before we get rolling? Everybody good? Everybody straight? All right. Okay. Not a problem. Thanks for letting me know. All right. Let's see. Where did we leave off? I think all we did was 5-1 last class. Let me see. Got 5-2 addition rule. Yeah. All right. So let's look at 5-2 today. Some, yeah. Let's look at 5-2 and probably 5-3 today. So we start off with the addition rule and complements. So two events are disjoint if they have no outcomes in common. And that's also called mutually exclusive events. So disjoint and mutually exclusive are used interchangeably. They mean the same thing. If an event is events are disjoint, they do not have anything in common. If events are mutually exclusive, once again, they do not have anything in common. All right. So here's our addition rule for disjoint events or mutually exclusive events. If E and F are disjoint, then you would take the probability of E. And so, well, let me say it like this. If you want to know the probability of E or F occurring, then you'll find the probability of E and find the probability of F, and then add them together. So once again, that's if the events do not have anything in common. They're considered mutually exclusive or they're considered disjoint. And you can just add their probabilities together to find the probability of either one of those occurring. All right, so before we get into a legit example, we want to make sure we explore the details of a deck of cards. Standard 52 card deck. And so standard 52 card deck means no jokers. So we have four suits: spades, clubs, diamonds, and hearts. Two of those suits are black, spades and clubs. Two are red, diamonds and hearts. 13 cards each suit. So you have 3 face cards and 10 regular cards. Your face cards are king, queen, jack. Your regular cards, ace, and then 2 through 10. So your ace is not a face. Ace is not a face card. All right, so I said something. Okay, cool. Not a problem at all. All right, is everybody done with the deck of cards? Can I scroll up? All right, so let's look at our first example. So suppose a single card selected from a standard 52 card deck. A, we want to compute the probability of drawing a king. Then we want to compute the probability of drawing a king, queen, or jack. So give you a chance to write that out. All right, so the first one we want to establish is the probability of drawing a king. Probability of drawing a king. So first thing, whenever you look to deal with any probability, remember we talked about last class, is that you want to establish the number of total possibilities. That's your sample space, the number of your sample space. So that's going to be 52 because there are 52 cards in the deck. Then you look at the number of your event. Our event is kings, drawing a king. So we want to know how many kings are in the deck. There's 4. There's 1 in each suit. So there's 52 cards in the deck total. There are 4 kings in the deck. All right, so once you have those two numbers, you take the number of your event, place it over the number of your sample space, 4 over 52. That's the probability of getting a king. And that'll be 1 over 13 once you reduce. All right, any problems with A? All right, so B is compute the probability of drawing a king, queen, or jack. So you notice the first statement that we look at B, these events are mutually exclusive, or in other words, disjoint. They do not have any cards in common. So there's no such thing as the king of queens or a queen of jacks or anything like that. So you have 4 kings, you have 4 queens, and you have 4 jacks. All of those are separate. They are not in common in any way. All right. So there are no kings that are queens. There are no jacks that are queens or no jacks that are kings and so on. All right. So since all of them are mutually exclusive, that means we can find their probabilities individually and then just add them together to find a probability that either one of them will occur. In other words, you pick out a king, queen, or jack. So it just so happens that, as far as the probability of getting a king, a queen, or a jack is going to be the same probability, right? Because you have 52 cards in the deck. So that's going to be the sample space for all 3 of them, right? That's not going to change. There are 52 cards in the deck, no matter which category you're looking at. Then there are 4 kings in the deck. There are 4 queens in the deck. Then there are 4 jacks in the deck. Once again, it's just because of the nature of what we're asking. That will not always be the case. It will always be the case for king, queens, and jacks. But let's say they ask you for what's the probability of getting a king or a heart, where there are more than 4 hearts. So that's what I meant by that number will not always be the same as far as that 4. There will always be 4 kings, but there are 13 hearts. So then you have to explore a different probability, and we'll look at that as we progress forward. But for this one, there are 4 kings, there are 4 jacks, there are 4 queens. I mean, four. Yeah, I said it right. 4 kings, 4 jacks, 4 queens, and then you put that 4 over 52, and then we add them together. To find the probability of king or queen or jack. So that ended up being 12 over 52. And then we can reduce that to 3 over 13. Any questions? All right, scroll up. All right, next one, a single die is tossed. Find the probability of rolling a number less than 3 or greater than 3. So once again, the first thing we want to establish is our sample space. I did that right here. You ever rolled a die or rolled some dice, playing Monopoly or any type of board game or something of that nature, there's 6 faces and, they have a pip for each number. So, you have 1, 2, 3, 4, 5, 6, and so on. So there are 6 possible outcomes for your die, a single die. So we have 2 events. We have less than 3 or greater than 3. So the numbers that are less than 3 is 1 and 2. So there's only 2 outcomes there. So that's right there. The number of numbers that are less than 3, 2. And so the probability of getting a number that's less than 3 would be 2 over 6. Remember our bottom number, our sample space is 6, so that's always our bottom number. So we're talking about 2 out of 6 chance of getting a number less than 2. Over here, we're exploring this event in the same way. This time, we're looking at numbers that are greater than 3. In our sample space, we're talking about 4, 5, and 6. So there are 3 numbers that are greater than 3. So that's 3 over 6 as a probability. All right, any problems before we finish it off, put it together?
So you don't reduce these, or do you?
No, it wouldn't. It would be in your best interest to wait till the end
Okay.
to do your reducing, because what's going to happen is if you reduce this right here, that'll turn to 1 over 3. You reduce this right here to turn into 1 over 2. Then when you add them together, you got to turn them back because you have to have common denominators. So you might as well just leave them like that. And so like if you go back here, we could have did the same thing here, reduced them first. In this case, because they were all the same thing, they would end up having the same number at the bottom anyway, would have been good. But I always say just reduce at the end, and that'll be the safest way. Save on some time. All right. So take that 2 over 6, add it to the 3 over 6, and that'll give us 5 over 6. That's our probability. All right. Any questions before we look at the general addition rule?
Could you scroll up a little bit, please?
Let me know when to stop.
Right there is fine.
Okay.
Thank you.
Mm-hmm.
Thank you. I'm good.
All right. Sounds good. Anybody else before we scroll up? All right. So we're looking at the general addition rule now. Now, the addition rule that we had before did not have this piece right here because they didn't have anything in common. But generally, and I'll say this, and if they don't have anything in common, then this piece would actually be 0. That's why we only had to worry about, just adding our probabilities together. But if we're looking at it generally, if events E and F are not mutually exclusive, that's when this come into play. That's the piece that includes what E and F have in common. And so you see that we're adding the probabilities and then we're going to subtract what they have in common. And you'll see why that has to occur in a second. So I'll show you an example that solidifies why we have to, subtract what they have in common. I'll give you guys a chance to write that down first. All right. Can we scroll up? Are we good? Oh, that's a good spot right there. So this next example, a single die is tossed. So we're going back to our single die. Find the probability of rolling an even number or a number less than 5. So we're looking at rolling an even number or a number less than 5. All right, is everybody good? Scrolling up. Okay. So first thing we want to do, as always, is establish our sample space. We already know from the first, or not from the first, but from the previous example that our sample space is going to be 6 when we're talking about a die. So we're good to go there. Now, our first event is rolling an even number. The even numbers that we have, 2, 4, and 6. So there are 3 even numbers. So we place that 3 over 6 as our probability for that event, rolling an even number. We'll get here in a second, but that's not where we're going next. We're going to the next event, which is rolling less than 5. So there are 4 numbers that are less than 5. When you're talking about 1 through 6, so we take that 4, place it over 6 for the probability of that event. So before we go any further, make sure we're okay with establishing the probability for a number less than 5, establishing the probability for an even number. So I want to give you a chance to get to that part. All right. So now we look at our events. We do have to ask ourselves, are these events mutually exclusive? Because remember, if they're mutually exclusive or disjoint, remember those two things mean the same thing. If they're mutually exclusive, all I have to do is add my probabilities together and I'm good to go. But first thing, if you notice, if you were to add 3, 6, and 4, 6 together, you get 7 over 6. That takes us over 1. But remember, our probabilities cannot exceed 1. So we know something is going on there. But if you look at what I wrote in the red, these events are not just disjoint. These events are not mutually exclusive because they have something in common. And if you notice, they have the numbers 2 and 4 in common. So they're not mutually exclusive. So that means we have to consider the probability of picking an even number and a number that's less than 5. In other words, 2 and 4. So once again, there are 2 numbers that are even and less than 5. So we take that number 2, like I said, because there's 2 numbers, and we place it over 6. So this is the probability of getting a number that's even and less than 5, 2 out of 6 chance. All right. So now, remember in the probability of calculating the probability of even or less, we have to subtract what they have in common. Well, you may want to say, well, why do you have to do that? Well, that's because in this probability right here, I'm counting 2 and 4. In this probability of 4, 6, I'm also counting 2 and 4. So if I were to add those probabilities together, I'm actually counting 2 and 4 twice. And that's not what we want to do. We don't want to include any number more than once when we're calculating our probability. So that's why we have to subtract what they have in common. So we don't count those events or don't count those elements twice. And so that brings us down here to this formula. And that's this piece right here, subtracting what they have in common. And that'll give us a 5 out of 6 chance of getting a number that's even or less than 5. All right. Any questions? Any questions? All right. Can I scroll up? So we have a single card is drawn from a standard 52 card deck. Compute the probability of the events of drawing a king or drawing a diamond. All right. So once again, we want to ask ourselves, are the events mutually exclusive? In this case, the answer is no, because there is such thing as the king of diamonds. So you want to know the probability of drawing a king or drawing a diamond. But once again, we don't want to count any card more than once. And there is a card that is a king and is a diamond, and that will be the king of diamonds. So these events are not mutually exclusive. So we are going to have to think about that subtracting piece. So here's the probability of each one of those events. So first of all, we recognize that, the probability, not a probability, the sample space of each is going to be 52 because there are 52 cards in the deck. All right. Then the next row, there are 4 kings, there are 13 diamonds, but there are also 1 king of diamonds. So it's a king and a diamond. And then from there, we go ahead and set up our probabilities. 4 out of 52, 13 out of 52, 1 out of 52. And once again, like your classmate mentioned, we will go ahead and leave them as they are right now, and then we will reduce later because we don't want to have to, if you reduce now, you're going to change, your denominator is going to end up being different, and then you got to take them back to this, all of them having the same denominator. So we'll calculate all the way to the end, and then we'll reduce at the end if possible. All right, any questions on anything before we scroll up? Once you have all 3 pieces, then you plug them into the formula. So it's 4 over 52 plus 13 over 52 minus the 1 over 52. So that'll give us 16 over 52, then reduced by 4, and that'll be 4 out of 13. Any questions? Any questions?
No.
All right. Thank you. Thank you. Anybody else before I scroll up? All right. So the complement of an event, all the outcomes in the sample space that are not in the event. So it's everything else. So if you have the probability, if you want to know the probability of a certain event, you can calculate that. Then if you want to know the complement, is everything else that could have occurred. So E with the superscript, E up, like a exponent with a C up, is going to represent the complement of your event E. So whatever you call your event, if you call your event L, then L with a C up there is how your book will label the complement of event L. All right, your complement rule is that if you want to find the probability of your complement, but you have the probability of your event, if you subtract it from 1, that will give you the probability of your complement. Or vice versa, if you know the complement, the probability of your complement, and you want to find the probability of your actual event, you can subtract that from 1. And then the other part of that relationship, that if you add the probability of your event and the probability of the complement of your event, they will equal to 1. So that relationship will always hold true. Your event and not your event will always add up together to give you 1. All right, can I scroll up? All right, according to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? All right. So 52% of Americans have played state lotteries. We want to know the probability that an American has not played. So it's just this simple. We know 52% has played. So if you convert that to a decimal, it's 0.52. If you want to know how many has not played, subtract that 0.52 from 1. It's 0.48. So, or you can write it as 48%. Any problems with that? All right, can I scroll up? All right, so let's look at 5.3. So we're looking at 5.3, independence and the multiplication rule. So two events are independent if the occurrence of one event does not affect the other. And then two events are dependent if the occurrence of one event does affect the other. All right. So the next exercise, we're gonna look at, a couple events and make sure we can determine whether events are independent or not. All right. Once again, independence and dependence is dependent upon or dictated by whether it affects the probability of another one occurring. All right. So suppose you flip a coin and roll a die. Are the events obtain a head and roll a 5 independent? So you're talking about flipping a coin, rolling the die. Does either one of those affect the probability of the other one occurring? So they are independent because one has nothing to do with the other. If I flip a coin, it has nothing to do with me rolling the die. Everybody okay with that? All right. So B, are the events earned a bachelor's degree and earned more than $100,000 per year independent? Earning a bachelor's degree and earning $100,000 a year, are they independent? All right, so no, they are not independent because earning a bachelor's degree increases your chances of earning $100,000 or more. Now, it doesn't make a guarantee, of course. We're talking about increasing your chances or increasing the probability that you may make, $100,000 or more. All right, any questions?
No.
All right, sounds good, sounds good. Everybody done writing? Can I scroll up? All right, so multiplication rule for independent events. Remember, last section we were looking at or. This time we're looking at and. So we wanted the probability of E or F happening. That's what we were dealing with the addition rule. This time we're looking at the probability of E and F happening. So in other words, if both of them happen, how we calculate the probability, we'll be using multiplication. And so now also notice that this is the multiplication for independent events. So it's something else, we have to do for, or something else we have to consider for dependent events. All right, can I scroll all the way up? Very good. All right. So in the game roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot number 17 two times in a row? So I'll give you a chance to write it down for those who are doing so. All right. All right. So the first thing we have to ask ourselves, are these events independent? Do they have anything to do with the next, does one row have anything to do with the next row? So these events are independent. The occurrence of rolling 17 does not have any effect on rolling 17 again. So it's not like they're going to put a blockage on rolling the 17 or remove any numbers out or anything like that is going to occur. So roll 17, then you just roll again, move the ball out of the way, roll again, or whatever the case may be. So these events are independent. Probability does not change. All right. So first thing we recognize is our sample space. We need to know the probability of rolling 17 the first time. There are 38 numbers in our sample space. If you were to go back, we have 0, 00, and then we have 1 through 36. So 1 through 36 is 36, plus 0 and 00 will be 38. So the total number of 38 options, 38 slots, and then rolling the 17. 17 is just one number. It's one of those 38 numbers. So the probability of rolling the 17 is 1 over 38 or 1 out of 38. All right. And so if we talk about the probability of rolling 17 twice, we want both of them to happen, not either or. That would be 1 over 17, 1 over 38 times 1 over 38. And that's 1 over 1444. And if they want the answer in decimal, my math lab let you know how they want the answer. They want it in decimal, they'll tell you how many decimal places to round up. But if they want it in fraction, then you would just write 1 over 1444.
Could you go back up to the Oh, that's good.
Okay. Any questions? Make sure we're all right. All right, are we good? Everybody good? All right, so the probability that a randomly selected 24-year-old male will survive the year is 0.9986, according to the National Vital Statistics Report. A, what is the probability that 3 randomly selected 24-year-old males will survive the year? B, what is the probability that 20 randomly selected 24-year-olds, or 24-year-old males will survive the year? Give you a chance to write that out. All right. So first thing, once again, we want to ask ourselves, are these events independent? The answer is yes, because someone surviving the year, a 24-year-old male surviving the year has nothing to do with another 24-year-old surviving the year. Of course, we're not talking about anything strange. Excuse me. If they know each other and somebody doing something to somebody, we're not talking about that type of stuff. We're just talking about randomly selected 24-year-old male surviving the year has nothing to do with another male surviving the year. So if that's the case, we know the probability of surviving for a 24-year-old male is 0.9986. If I scroll up too far, let me know. So we're looking at the probability that all 3 survive. So we're looking at multiplying those probabilities together. And you can put it in your calculator by 0.986 raised to the 3rd power. And so that'll be 0.9958. All right. Any problems with that? And then B, the probability that all 20 survive, just raise that 0.9986 to the 20th power. And that'll be 0.9724. So it's important that you know how to use your calculator. Some calculators each calculator has different functions, could have this as your function. You may have seen that. So that means you can put 0.9986 in the bottom, 20 up top, or you can use this caret or hat, depending on who you're talking to, whether they call it caret or hat, and then raise it to the 20th power. So different calculators have different functions that you can use. If you ever have any questions about your calculator, always feel free, to ask, and I can do what I can to help you out. Any questions or A or B? All right, let's scroll up. Everybody good? All right, so here's the probability that at least one male out of 1,024-year-old males will die during the course of the year. If the probability that a randomly selected 24-year-old male survives the year is 0.9986. All right. So we're going to use the complement rule here. We know that 0.9986 represents that 24-year-old male surviving the year. Now, if I raise that to the 1,000 power, that's going to represent that none of them died. But we want the probability that at least one would die. So we would do 1 minus the probability that none of them will die. And so that's how we would calculate that. That's 1 minus 0.9986 raised to the 1,000 power. It gives you 0.2464. Then 1 minus 0.2464 is 0.7536. And that probability represents at least one die. You know, maybe 2 die, 3 die, 4, you know, all of the, you know, chances, you know, other than everybody surviving. Everything else other than everyone surviving. Excuse me. Any questions? Any questions? I think that's it. Yeah. Very good. Can I come off this page? Let me see. Yeah. Let's see how. Yeah. Okay, so that's 5253. I think, do I want to do 5-4 now or next class? Yeah, I think we'll just go ahead and do 5-4 today. And then next class, we'll just start in 6. Okay. So yeah, let's go ahead and knock out 5-4 since we have you know, plenty of time. So 5-4 is conditional probability and the general multiplication rule. So now we're looking at the possibility of having dependent events. All right. So here we have the probability of F given that E has already occurred. So that's the symbolism there. This long bar in between F and E, is going to be the probability that F occurs given that E has already occurred. All right, so the way we would calculate the probability of F given E has occurred, either we have the probabilities or we have the number of those events. And so it's the probability of E and F over the probability of E, or the number of E and F over the number of E. So the positions, of this does matter, and that will alter your probability. Whether you want to find the probability that E occurs given that the probability that F occurs given that E has occurred, or if you find the probability that E occurs given that F has occurred, there will be two different probabilities. So, and we'll put numbers on it in a second. And I'll scroll up. So this chart represents the marital status of males and females 15 years or older in the United States. So it's in millions. So we got never married, married, widowed, divorced, separated, and then the totals at the bottom. Then we have males, females, and totals for our columns. Got 41.6, 64.4, 3.1, 11.0, 2.4, and that's 122.5. Then we got 36.9, 63.1, 11.2, 14.4, 3.2, and then 128.8. Then that final column, 78.5, 127.5, 14.3, 25.4, 5.6, 251.3. I'll give you a chance to write that down. All right, can you scroll up? All right, so it says use the table to answer the following. It says compute the probability that a randomly selected individual has never married given the individual is male. Let's see that right now. Okay. Then compute the probability that a randomly selected individual is male given that the individual has never married. All right. So I'm going to call N never married and M male. So what do you want us to find first? is the probability that the person chosen, the randomly selected person chosen, was never married, given the individual is male. So if you talk about never married, given male. So I'm looking for the number that fits the category of never married and male. And then down here, I'm looking at the number of males. So never married and male would be right here, 41.6. And then the total number of males, 122.5. And so that's what I did right here. And divide that out, gives you 0.34. So that's the probability that a randomly selected person chosen was never married, given that they were male. Any problems with what we did there? All right, so for B, let's make sure we are looking for an individual as male, given the individual has never married. So this time we're flipping them. Still using M for male, N for never married. But this time it's male, given, never married. So I need the number of males and never married. But then on bottom, we're looking at the number of never married in total. So going back up here, never married in male still 41.6, but never married in total is 78.5. And so that's what I did, 41.6 over 78.5, and that's 0.53 out of 53% chance. All right, any questions? All right, so the next one, suppose that 12%, 12.7% of all births are preterm. Also 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? And then is this unusual? All right, so once again, 12.7% of all births are preterm, 0.22% of all births result in a baby who weighed, preterm baby who weighed 8 pounds, 13 ounces or more. So right here, I decided to call W, weighs 8 pounds, 13 ounces or more, called P, preterm. All right, so the probability of getting a preterm baby is 12.7%. So go ahead and convert that to a decimal, is 0.127. And then the probability of having a baby that's preterm and weighing 8 pounds, 13 ounces or more is 0.22%. Converting that to a decimal is 0.0022. And that information we all got from the problem. So now we want to know what's the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm. So that's this setup right here. 8 pounds, 8 ounces, 8 pounds, 13 ounces or more, given that's preterm. So that means we need to do P and W. That's my top number. And then the probability of P is on bottom. All right. So that's 0.0022 on top, 0.127 on bottom. And that will calculate, give me 0.0173. Any problems? All right, 0.0173 is the same thing as 1.73%. And remember the last statement was, is this unusual? And the answer is going to be yes, because the probability is less than 5%. Remember that was our marker for something being unusual or not. It was 0.05 or 5%. Something less than that, then it is considered unusual. All right, any problems? All right, can we scroll up? All right, so our general multiplication rule, if you want to know the probability of E and F occurring, find the probability of E, then the probability of F, given that E has already occurred. And remember before, we didn't have to worry about this because we had independent events. So the probability that E occurs has nothing to do with the probability of F occurring. But if the probability of E affects the probability of F, then we do have to consider that. So that's why this is the general multiplication rule. So here we have the probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket given that he or she is pulled over is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? All right, let's look at the given information called T getting a ticket and P pulled over. So the probability of getting pulled over is 0.8. And then probability of getting a ticket given that he or she is pulled over is 0.9. So that's the given information. I just put, letters to it. All right. So the probability of P and T occurring, or if you get pulled over and getting the ticket. First of all, you take the probability of getting pulled over and then the probability of getting a ticket given that you got pulled over. Multiply those together and that'll be 0.72. Any problems with that? All right, almost finished. But still holding on to the red. All right. So in a study to determine whether preferences for self are more or less prevalent than preferences for others, researchers asked individuals to identify the person who is most valuable and likable to you or your favorite other. Of 1,519 individuals surveyed, 42 had chosen themselves. Give you a chance to write that down. All right, can we scroll up?
Excuse me, can you hear me?
All right, so looking at A, suppose we randomly select one out of 1,519 individuals. What is the probability that he or she had chosen self or favorite, a self as a favorite other? So I give you a chance to write that as well. All right, so let's look at A. And then if I scroll up too far, of course, let me know. Suppose we randomly select one out of 1,519 individuals. What's the probability that he or she had chosen self as a favorite other? So first, we recognize that our sample space is 1,519. That's how many people we have. And we know that 42 chose themselves as their favorite other, their favorite person to be around, right? So the probability that someone chose themselves is going to be 42 out of that 1,519. That's all it is for that one. Everybody okay with A?
Yes.
All right, thank you, thank you. Miss Hunter, is that a scene from okay, think Hollow Knights?
Yes, sir.
I thought so. B, if two individuals from this group are randomly selected, what is the probability that both chose self? All right. So the way that we're looking at this, what's the probability that the first one chose self and the second one chose self? So the probability that the first chose self, we already, examined that. That's 42 out of the 1519. But then the second one is the probability that the second one chose self, given that the first one you chose self as well. So that one's going to be a little different. So, like I said, the first one is 42 over 1519. But then the next one, that second probability is going to be 41 out of 1518. And so where that comes from is if the first one you chose was someone who chose self, well, now there's only 41 out of the 42 people left. And then also out of the 1519, there's only 1518 left. So basically, you're asking yourself how many is left out of each one of those categories. One was taken out of each. Once again, you had 42 people that chose self. That's how many you had at your disposal from the first probability. If you take one of those people out, then there's 41 left. Then also at the bottom, there was 1519, but if you take one of those people out of those 42, there's only 1518 left. So that's why there's one taken out of each one of those categories. So before we go any further, is everybody okay with that? Make sure we're okay. So if you were to multiply those two together, you will get 0.000746 All right. Any problems? Any problems? All right. Then C, compute the probability of randomly selecting two individuals from this group who is selected, who selected self, assuming independence. So the key word here, or the key phrase here, is that we're going to assume independence. These two events are independent of each other. So that means one probability or one occurring does not affect the other one's probability of occurring. So we know the first one is 42 over 1519. But if the other one is not affected by what happens in the first probability, that one would be 42 over 1519 as well. It would have the same probability because nothing would change it. Nothing changed. And so then you would just multiply those two together, and that'd be 0.007645 as your probability. All right. Any problems? Any problems? Questions? All right. So everybody's good. Everybody's straight. So that's it for chapter 5. So make sure you try the stuff out. See if you have any questions. See if you get stuck on anything. We're going to look to get into chapter 6 and then also talk about how we're going to do our tests for this third one. But yep. So make sure you guys get in there. Is everybody good before we? Everybody good before we close out? Everybody straight? All right. So you guys have a good one. Be safe, and I will see you on Wednesday.
Professor Tucker, can I talk to you when everyone leaves out?
Sure.
Thank you.
Happy belated Father's Day.
Oh,
Bye.
thanks. I know y'all
Oh
hear the
yeah,
baby
happy
back
Father's
there.
Day.
Look, I know y'all hear them kids back there. I'll be muting and be able to fuss at them, but hoping the mute don't fail me. Say what?
I already know. That's what's up, though. All right.
All right, you take care. Thanks for that. Y'all
All
have a
right.
good one. All right, let me stop the recording.